Hi, I am Ambrozio, and this is my contribution to the first geometric analysis festival, organized by Hojo Lee from the Jeonbuk National University in South Korea. The name of my talk is Systolic and Diastolic Invariants related to minimal surfaces. This is video number 1. And the plan is to do the general introduction. So, in this video, I will be mostly talking about facts that I believe are very familiar to you. And my motivation to do this is not to talk about these results themselves, but to actually cast a certain light over them. And my motivation to this is so that the sort of question, the sort of vision that I will ask later will make some sense to you, at least from a perspective that's not strictly mathematical, but somehow still valid when one sits down to do research. I like to start talks where I like to give talks where I can start by quoting a theorem that most people knows and most people learn to love. And I am also lecturing this term a course on the geometry of curves and surfaces. So I decided to begin my talk with the Gauss-Bonnet Theorem. Okay, if we have a closed orientable surface with a Riemannian metric G, then the integral of the Gaussian curvature of the surface is equal to 2 pi times the Euler characteristic of the surface, which is equal to 2 minus 2 times the genus of the surface. Okay, the Gauss-Bonnet is this beautiful theorem, and part of the fascination with it is of course the fact that it is establishing an equality between two objects that have a different nature. So from one side we see geometry, and from the other side we see only topology. There are other formulae like this for higher dimensional manifolds, but this kind of integral formula is not the only way that we know to establish a relationship between geometry and topology. So now I want to talk a bit about how can we use geometry to understand topology, and which is an aspect, right? So of Gauss-Bonnet theorem. Given a smooth manifold M, there are topological invariants of M which are representable by submanifolds of M. So for example, the fundamental group is a topological invariant, a group that is made out of equivalence classes of closed curves inside Mn. There is also the homology theory, where the objects that represent those groups are submanifolds of Mn. Okay, and there are also other topological invariants that are representable by, say, differentiable forms. So for example, the cohomology or the Chern classes. And I am mentioning those topological invariants in particular because the objects that represent them are suitable and they can be measured once we introduce some geometry, right? So once we introduce geometry, we can quantify, right? So those topological invariants by making measurements. So by using geometry, we can pick a best representative of those classes of objects that are representing non-trivial topology of the manifold. And by studying the geometry of the best representative, and together with the geometry of M itself, we may be able to decide if a topological invariant is trivial or not. Okay, this is a well-known idea. In the next slide I will show you it working in practice, but before that let me mention, right, that by doing this, beyond understanding the interactions between topology and geometry, we can define geometric invariants now that are interesting on their own. So interesting that we might be wanting to compare it to other invariants like the diameter, the injectivity radius, the volume, the curvature, so the other geometric invariants that are more familiar to us. So let me then now show you an example of this two-step program on how to use geometry to understand topology. And to show you how it works more or less, I will talk about one forms. So take Mn, orientable closed manifolds of dimension n, and let omega bar be a closed differentiable one form, meaning that its exterior differential is equal to 0. So by deforming it by the differential of smooth functions on n, we define a class that is a representative of the Dehaene first cohomology group. Now, if the class defined by omega bar is non-trivial, we can use geometry to measure how non-trivial it is with respect to a given metric G. So we can introduce this functional, we compute the L2 norm of omega, and we minimize and compute the infimum among elements or among one forms that represent this cohomology class defined by omega bar. Okay, so if the cohomology class is non-trivial, this number is positive, and this infimum is attained by a unique one form omega 0, which because of the fact it is a minimum, satisfies a geometric condition. So not only it is a closed one form, its divergence with respect to the given metric G is equal to 0. Okay, now we use geometry to study this minimizer, omega 0, and we deduce a formula, an integral formula, so which I wrote there, where the Ricci curvature of the Riemannian metric G appears. And notice that the first term in the integral is non-negative. So if Ricci is positive, this inequality cannot hold for non-trivial omega zeros. Okay, so what this is saying that if the Ricci curvature is positive, the first Dehaene cohomology of the manifold must be equal to 0. Or more precisely even, if my closed orientable manifold M admits a metric G with positive Ricci, then its first cohomology group, the group, is trivial. Okay, and this is well, a concrete example of the general idea that I described. And by the way, if you recall that the first cohomology group of an orientable surface has dimension equal to twice the genus, you will see that the conclusion here that you used in one form is the same conclusion as that you could have deduced using the Gauss-Bonnet formula. Namely, that a surface with positive Gaussian curvature must be a genus zero surface, that is a sphere. Okay, so so these are general ideas. Now I want to talk about a certain metaphor, a metaphor that was introduced in mathematics by Marcel Berger. So Marcel Berger used the term isosystolic inequality to describe a class of inequalities, like Poole's inequality, which we'll be talking about in video number 2 actually. And what is the meaning of isosystolic? So he was thinking about what he's called the systole of a surface, namely the least length of a closed curve that is non-trivial in the first fundamental group. So he was thinking about this systole compared to the volume of the surface. Okay, so when he talked about isosystolic, he is thinking about the systole of surfaces that have the same volume. Okay, and where did this analogy, this metaphor came from? So it came from biology. So in biology, well, we know, right? So our heart is beating periodically, and in biology, the doctors or the scientists distinguish between two moments of this periodic movement. So there is the moment of contraction, which they call the systole, and there is the moment of expansion, which is the diastole. Okay, so if you think about the homotopically non-trivial closed curves in a surface, and you imagine them contracting as much as they can, so that we get this least length that Berger was talking about, you can see that systole is somehow a nice metaphor to describe this number, right? The least length among homotopically non-trivial closed curves. And well, but how about the diastole, right? So what kind of invariant we could think of as a diastole? I want to show you one that I would argue looks pretty much like a diastole. And this is the first Laplace eigenvalue. So let's take Mn, a closed Riemannian manifold. Let's put a Riemannian metric on it and define the Laplace operator acting on smooth functions on M. So minus the Laplacian is an elliptic operator. There are eigenvalues and eigenfunctions. So eigenvalues are numbers, lambdas, such that this equation has non-trivial solutions that are called eigenfunctions associated to the given lambda. Okay, so multiplying this equation by phi itself and integrating by phi parts is not difficult to see that lambda has to be non-negative, and 0 if and only if the corresponding eigenfunction is constant. So this is true for all manifolds and all metrics. So what is interesting to look at is the next eigenvalue. So this is called the lambda 1. This is the smallest positive eigenvalue of MNG. So now let me describe how one can compute this lambda 1. So on the Sobolev space W12 of functions on Mn, it makes sense to define the following functional. So we can take a function in there, integrate the square norm of the gradient, and divide by the integral of the square of the function itself. So the variational characterization of lambda 1 is that lambda 1 is equal to the infimum of this functional among all W12 surface functions that are non-zero and integrate to 0. So I will leave you as an exercise to show that this infimum of this functional, this is called the Hailey quotient, is attained by a function phi that is the corresponding eigenfunction to lambda 1. Okay? Okay, so this characterization describes lambda 1 as the infimum of a functional on a given linear subset of the Sobolev space W12. So you may think, well, in a sense, this is similar to what Berger was thinking about with Systos. So he was minimizing the length of homotopically non-trivial closed curves. However, I think that this formula obscures a bit the real character of lambda 1. And this second variational characterization is the one that I think is the one that is interesting for us in this discussion. And what is this characterization? So I will take capital C to be the set of all continuous families of maps on W12 except the origin, such that the initial map is constant and equals to -1, as the final map is constant and equal to 1. So for all these families, since the integral of phi t is varying continuously with t, and since I begin with a function with negative average and I end with a function with positive average, of course, there will be a time t where I pass this family, will pass through a function which has zero average. So this function will be such that the Hailey quotient is at least as big as lambda 1. Now, given this observation, it's clear that this min-max quantity that I defined here is at least as big as lambda 1, right? So for each family in C, I compute the maximum of the Hailey quotient of the functions in the family, phi t, and then I take the infimum over all such families. I said that this is an inequality, but actually you can construct an explicit family where the maximum is attained by the first eigenfunction of lambda 1, and therefore this infimum is actually a minimum, and equality holds. Okay, so and this is kind of the characterization of lambda 1 that I find interesting. So notice that the Harmonic quotient doesn't see the difference between functions that are multiple of each other, and somehow what we are doing here is exploiting the non-trivial topology of the space W12 minus the origin modulo scaling. Okay, and also notice that the Harmonic quotient of constant function minus 1 and constant function 1 is equal to 0, right? So this family, from the point of view of the Harmonic quotient, is sort of a loop starting off the absolute minimum of the Harmonic quotient and going through some hole on which it gets stuck. So we found lambda 1 as a mountain pass or a min-max critical value of the Harmonic quotient. Okay, and well, this is the point that I wanted to arrive to. Coming back to the metaphor, so remember that the systole is the moment of contraction of the heart and the diastole is the moment of expansion. I want to propose an expanded metaphor, which is, in geometry, I would say that a systolic invariant is an invariant that captures non-trivial topology of the manifold M itself and is the minimum value of a geometric function. And I will say that a diastolic invariant captures non-trivial topology of spaces of objects on M and is a one-parameter or mountain pass critical, a one-parameter min-max or a mountain pass critical value of a geometric function. Right? So I hope that I convinced you that this movement of expansion has the right analogy in the example of lambda 1, and in the next talks we will see systolic invariants and diastolic invariants that are related to the area function. So yes, just be cautious, sorry. This should be thought just as a metaphor. This is not anything deep that I'm saying here. It's just a metaphor that I came up with. But anyway, I think it's somehow nice to think in this way. Okay, so now let me try to move on to a mathematical problem. What I want to do is to understand how the systolic and diastolic invariants of a Riemannian manifolds, when they are compared to the total volume of the manifold, behave as the Riemannian metric on a given manifold changes. And more precisely, I will be concerned in my talk about the comparison between the total volume of M and G to systolic and diastolic invariants of M and G that are related to the area functional and minimal submanifolds. Okay, this is the end of the first talk. Thank you for your attention.